The name of this video is Case 2 Examples. What we intend to do in this video is to consider a couple of examples and verify the local form case 2 of Maxwell's equations for the electrostatic field E. The procedure will be as follows. We consider a particular example with a charge distribution. We attempt to solve quickly that problem by some means, and then eventually we try to use the solution to verify the local form of Maxwell's equations. All right. The first example we want to consider is to revisit the case of an infinite charged plane, which we already solved by means of Coulomb's law and the superposition principle. This time, however, I will want to solve it using symmetry arguments and Gauss's theorem. So let us consider again an infinite plane of charge. As such, this plane extends all the way to infinity, represented by these dashed lines. This plane, we call it capital sigma, is identified by an infinite surface capital sigma with a surface charge distribution with constant density small sigma. This is constant. It's the same as we did using Coulomb's law and the superposition principle. So first off, we want to revisit this problem in order to find the electrostatic field E at any point in space, capital P, anywhere, but by means of symmetry arguments and Gauss's theorem, instead of Coulomb's law and the superposition principle. So, as always, the first step is to identify a proper and suitable coordinate system. So this is the center, the origin. We want typically this to be the z-axis. This is the origin, the axis continues all the way here. This is our y-axis. We want the right-hand rule, so this will be the x-axis. X, Y, Z. And this is the origin right there. All right, great. So we chose one specific coordinate system, a Cartesian coordinate system of x, y, z. Now we want to use symmetry arguments in order to find all the components in this Cartesian coordinate system of the electrostatic field E. What are all the symmetries of an infinite plane of charge, in general of an infinite plane? I'm an observer, observing this plane which is equal everywhere in space, all the way to infinite. So obviously we can translate it left and right along the x-axis by any displacement we want. So this is a translation along the x-axis of any displacement we want. Similarly, we can translate it up and down along the y-axis by any displacement we want. By means of these two translations, we obtain planes which are identical because this plane is infinite. As it turns out, these two translation symmetries are the same as a rotation symmetry by any angle in any direction about the z-axis, because I can also consider this infinite plane as if it were an infinite disk with infinite radius. So when we rotate it like this, we obtain exactly the same plane. So this is the same as this. So these are the same as this. All right. So this is one set of symmetries. We also have two other rotation symmetries. We can rotate about the y-axis, about the x-axis by any angle minus plus pi. And we can rotate about the y-axis by any angle minus plus pi as well. These are all the possible symmetries associated with this infinite plane of charge. Now that we know the symmetries, we want to examine some of the components, in principle all of them. I will do only two of them, I'll let you do the third one. So let us pick a point, capital P, let's say on the z-axis, doesn't have to be, but for simplicity, let's say here. This is my point capital P. And there, I will have, for example, a y component Ey, like this, and a z component Ez, like this. And I will actually do the same argument for the x component, for example. Okay, let's start with the z component, Ez. So if we perform any rotation by any angle bar phi about the z-axis or any translation by any displacement along x or y, that is, if we span any point on this new parallel plane here, plane parallel to capital sigma, we will find out that the component Ez has to be the same at each point on this plane. So this Ez has to be the same as this Ez. Okay, similarly for Ey, also Ey has to be the same at each point on this plane parallel to capital sigma because of these translation symmetries or this rotation symmetry about z by any angle bar phi. All right, now for example, the next thing we can do, we can perform a rotation about the x-axis by an angle pi. This is step one. We go from here to here. So clearly z, if I pick a point here, exactly the opposite of this point, so I pick a point here, Ez will become this new vector. What about Ey? Ey will become this new vector. Now, for example, we can perform a rotation about the x-axis about the y-axis by any angle, let's say in this case plus pi. This is step two. So here we rotated about the x-axis by an angle pi, and here we rotate about the y-axis by an angle pi. So this vector z becomes exactly the vector we began with. Whereas the vector Ey becomes the opposite of the vector we began with. Clearly, Ez is consistent with all the symmetries of this problem, whereas Ey is not. This means that Ey, and in fact, I will let you prove that this is also true for Ex. So this, you can prove it and discuss about it in Piazza. They both have to be equal to 0. So these components, x and y, are 0, whereas z can exist, and if it does, is directed along the z direction on the right-hand side, and we call the right-hand side as region 1, whereas it's directed opposite to the z direction in region 2, which is the negative region on the left-hand side. And as you can see, I'm already going into these regions 2 and 1 because I want to verify the local form case 2 of Maxwell's equations, where we need 2 and 1. All right, so now we are in a position where we can actually write down we can solve for z by means of Gauss's theorem. So far we only use symmetry arguments, and now we want to use Gauss's theorem to find quantitatively the value z. So for this you can follow a couple of different approaches. So you can either use, we need to define a Gaussian surface which contains somehow a region on the plane capital sigma. So you could choose something which is a little cylinder. So this would be the trace of the cylinder, and the cylinder can be like this. And then I go to the negative side in the region 2, and you can, this would be an area, the cross-sectional area of this Gaussian surface on capital sigma, or, for example, for pedagogical reasons, let us consider a cross-section which looks more like this. Like a parallelepiped. And then it also extends on the negative side. For example, let's stop it there. All right. So this is a parallelepiped, which again has this as cross-sectional area with capital sigma. For example, we can say that this distance here is dx, whereas this distance here is dy. So this little area is dx dy. And there is a little charge sigma dx dy contained on this region here. Sigma dx dy is the total charge contained within this parallelepiped, which is partially in vacuum in region 1, partially in vacuum in region 2, and it contains this little surface of charge, sigma dx dy. Okay. So now, what we want to do, we want to use Gauss's theorem to find E, Ez. So we know that on this face, Ez points, of course, in this direction, whereas on this face, it points, of course, in this direction. There are no other contribution on the lateral surface because all the x and y are 0, and z there is normal to any normal unit vector which points outside the surface. And so the only contributions, obviously, are from these two regions. So Gauss's theorem simply becomes the integral, the surface integral on the area dx dy of Ez. I'm looking at this one first. This is positive, so it goes along the z direction. I need to dot it with uz, which is the normal unit vector, times dx dy, okay? The area, which is infinitesimally small in this case. Actually, probably is more proper, let's call it simply dA. Let us just call this one dA, okay? So as always, when we do the integral of an Ez on an infinitesimal surface, we can say that this Ez is constant, so we can take it outside the sign of integral. This area and this area are infinitesimally small, so this basically becomes nothing but Ez uz dot uz is 1 times dx dy. Similar on the other side, we have minus Ez directed as uz in the opposite direction of this vector here. This we need to dot it with a negative uz, the flux goes also in that direction, times dx dy. And so this gives us minus minus is plus, plus Ez dx dy. And we know that there is no other contribution, so this has to be equal to Gauss's theorem, 1 over epsilon naught, the total charge contained within that cylinder, which is sigma dx dy divided by epsilon naught. All right, so obviously in this case, dx dy, we can cancel it out. We can cancel it out here. And so we are left simply with 2 times Ez equals sigma over epsilon naught. And so as expected, we already found this result by means of Coulomb's law and the superposition principle. We simply obtain Ez equals sigma over 2 times epsilon naught. Great. So we recover exactly the same result we found by means of Coulomb's law and the superposition principle. Great. So now that we have this result at hand, we can attempt to verify Maxwell's equations in local form case 2. So let's begin with the first one, which is the normal components of E, that is E1 minus E2, projected along n to 1. What is n to 1 in this case? Religiously, we always go from region 2 to region 1. So with respect to this coordinate system, n from 2 to 1 obviously points in the same direction as uz. Great, so we know that. This, in fact, we can also, typically people also write it as after projecting as En1 minus En2, so the normal component of the electrostatic field. Okay, so what are these normal components? So let's rewrite this with respect. We know from Maxwell equation case 2 in local form that this has to be sigma over epsilon naught. So we want to verify that this is correct. Well, let's write down, let's spell out this equation using this solution for the electrostatic field up here with respect to this coordinate system. So once we do that, in region 1, E1 is nothing but Ez pointing in the z direction, so times uz. What about E2? E2 is minus, we need a minus from this law, but then E2 in this region is minus Ez pointing along z in the opposite direction. This we need to project it along the n to 1 direction, which is plus uz. In this fashion. Minus is plus. Now we can substitute this value, sigma over 2 epsilon naught. So we obtain Ez plus Ez, that is 2 times Ez. uz dot uz, of course, is 1. This is nothing but 2 times this quantity, which is sigma over epsilon naught, which is exactly what we wanted to verify. Note that again, in this case, I really wanted to show you how to do this with respect to a specific coordinate system. Okay? In fact, we could have started from this law to attempt to find the z component instead of using Gauss's theorem with symmetry arguments, but I prefer to go in this way and just verify the local form a posteriori. The other scenario is quite easy, the other law, the other Maxwell equation in case 2 in local form, because that tells us that E1 minus E2, when projected along T to 1, this has to be equal to 0. Well, in this case, this one is quite easy, because what are the tangent components? Note that people also write this as the tangent component Et1 minus the tangent component Et2 equal to 0. What are the tangent components? They're nothing but Ex and Ey. Ex and Ey define a component which is parallel to capital sigma, which means it's tangent to capital sigma. Okay, so t goes in this direction, this plane, and so obviously E1 and E2 are 0. So it is clear that from this, also this equation here is fulfilled. And so to recap, we started from the problem of the infinite plane of charge. We solved by means of symmetry arguments, which allowed us to find that the only component that can exist that is self-consistent is Ez. We then use Gauss's theorem to find Ez, which we already found by means of Coulomb's law, the superposition principle. And then finally, we verify a posteriori the case 2 of Maxwell's equations, which is the discontinuity of the normal components, Gauss's theorem, and the continuity of the tangent components is actually fulfilled in this case. And I remind you that in the video about the Coulomb's law, the superposition principle solution, I also clearly sketched the E field for this plane, and I've shown you that the discontinuity, a discontinuity of the first kind at this boundary capital sigma is exactly sigma over epsilon naught. All right, the next example is that of a charged shell, which we already encountered in a home assignment. So let me recap here what is the electrostatic field in this case. Is the center of the shell. The shell is empty inside and outside. There is only a surface charge density small sigma on a capital sigma surface. The radius of this shell is, as always, capital R. Let us choose a spherical coordinate system where this is the radial axis R. I will not sketch theta and bar phi, but it's a spherical coordinate system OR theta bar phi. This is the origin of this system. Great. For a simple shell like this, I will just remind you that the electrostatic field, and here I'm doing a typical thing in science. This is the r-axis, but it is also the coordinate of the field. So I will show the magnitude of the field in one simple graph. This is very common in science. You need to get used to these kind of sketches. So this is the only possible component of the electrostatic field for a spherical symmetry is ER. Okay? And let's pick in particular this point here. Let's say that the critical point here. Great. All right. So the electrostatic field inside the charge shell obviously is zero because there is no charge inside. You can use symmetry arguments, Gauss's theorem. So the field inside is zero all the way to this point, whereas outside it starts from a certain point and it goes all the way down as if it were a single point-like charge in space concentrated at the point O. So if the charge on this shell is Q, we know that Q divided by 4 pi capital R square is sigma naught, okay? The charge density constant on this shell. So in this case, outside it behaves, according to Coulomb's law, as 1 over R square, all the way to infinity. Let's write it down a little bit more properly down here. So if we write down this a little bit more properly, we eventually find that the electrostatic field E is a vector which comprises the following components: ER equal 0 inside the sphere, which means for each point R from the origin from 0 all the way to capital R excluded. We will see now it has to be excluded. In addition, we know that ER has to be, according to Coulomb's law, if you want you can do very quickly, is 1 over 4 pi epsilon naught Q divided by R square. So it has to go as R square here, as R minus 2, 1 over R square, obviously, times UR, which is the direction we want to have in this case. All right, this can be rewritten in terms of sigma naught. So if I divide it in terms of sigma naught, I'm going to obtain sigma naught divided by epsilon naught times capital R square divided by small r square, where capital R square is the radius square of the shell. And finally, we know that E theta equal E bar phi equals 0. This is UR. This is 0. For R it goes from 0 all the way to plus infinite, whereas here R is from capital R to plus infinite. Great. This is our field. That's the way we sketch it. So let us verify. In this case, let's begin with Gauss's theorem in local form case 2. So if we do that, we obtain, first of all, we need to identify our two regions. So let's say that the region inside the shell is region 2, outside is region 1, which means that n to 1, from region 2 to region 1, is in this coordinate system nothing but UR. So with respect to this coordinate system, we can finally write down here E1 minus E2 dotted with N12, N21, 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 obviously. With respect to this coordinate system, E1, it's in the region outside, so this is given by this quantity here. So it's sigma in the limit, not that we need to go in the limit, approaching this point from the outside. So we're approaching from the outside, which means from the plus side. So we need to perform the limit for small r that goes to capital R plus from the outside. I'm approaching r from the outside, so plus of sigma naught divided by epsilon naught, capital R squared divided by small r squared, then we do the limit, so it becomes 1, this ratio. This is directed as UR, minus E2, which is 0, directed as UR, and this quantity I need to project it along N21, which is also UR. So as a result, what we obtain here, we obtain sigma naught over epsilon naught. This gives us 1. UR dot UR is 1. 0, obviously, does not contribute. So we simply obtain sigma naught divided by epsilon naught, which is exactly what we expected from case 2. Obviously, the other case for the rotational property clearly gives us 0 because the tangent components are obviously 0. So it is clear that E1 minus E2 dot T21 is equal to 0 because all the tangent components, which are theta and 5, are 0. Great. So we check this first example, the second example. The last example, it's actually something a little bit different, which I want you to meditate about. Similar to this, so in all these first two examples, we had vacuum, so nothing, surface, nothing. Here we had nothing, the sphere nothing, in the plane we have nothing, the plane nothing. What happens if I have something similar, but I have a hard sphere instead of a shell? So this one was a shell with charge Q. Now let's consider a hard sphere, which we also encountered in the home assignments. So in this case, the situation is a little bit different. Is this a surface boundary? Not. So do we expect to find the same results as case 2 for a surface? Maybe not. Let's verify that we don't. And I will give you also there a nice conjecture again on that. So let's consider a hard sphere. So we do the same thing here. So we have exactly our hard sphere with radius capital R, but now this is completely full everywhere. Great. So then we consider our coordinate system, which is R as always. And as always, I have the origin here, R, theta, var phi, a spherical coordinate system exactly as this one here. I will not sketch theta and var phi. So in this case, the usual sketch again, which I know people get confused, but you really need to get used to this way of sketching it. So I'm sketching the problem itself as well as the result in the same sketch. Okay, so don't get confused by that. It's very common in physics. Get used to that. So this is the only component which, again, for the same symmetry arguments which you were supposed to do in the home assignment. This is my ER, okay? So let's pick again this point here. Okay, here I left on purpose, let's do it bigger, an open circle because, as you can see, I'm not including this point here. So capital R, it's a discontinuity, so I leave it open. Here I already know that it's not going to be a discontinuity, so I keep it closed. Let's verify that this is the case. So what does it look, the field, the electrostatic field for a sphere? Well, this I will not do any calculation, I remember what it is. And so in this case, the electrostatic field, if the charge again is Q, so if we have Q, in this case, divided by the volume, which is 4/3 pi r cube, we call this rho naught, okay? So in this case, we obtain that the field E the electrostatic field E will be given by, all right, so it's going to be ER equal, inside the sphere, it goes linearly in this fashion. So it goes typical of hard spheres, so we'll see this over and over, is rho naught divided by the well-known 3 epsilon naught factor. Every time there is a hard sphere, there is a 3 epsilon naught in the denominator, always. We'll see this in dielectric materials, magnetic materials, rho naught over 3 epsilon naught. It has to be linear, it has to be coulombs over meter square, so I need to do this times r, and this goes as ur, all right? And this is defined for r in the region from the origin to capital R. Let me not put anything there. We will close this parenthesis at the end. What about the region outside? So as always, this is region 2. This is region 1. So basically this is region 2 if you want. Now let's do region 1. In region 1, we obtain the same prefactor, rho naught over 3 epsilon naught. Well, now it has to be Coulomb's law. So it's q over r squared, but if I substitute with this q, with this rho naught, it becomes simply capital R cube divided by r squared, small r squared. It is Coulomb's law, obviously, so it has to be like this, all the way to infinity. It goes again as r over minus 2, exactly like there. So here is linear, goes as r. This is in direction of ur, and this is in region 2, which is from capital R, I will use the parenthesis at the end, to plus infinite. This is region, sorry, 1. This is 2, this is 1. Great. And as always, the theta and bar phi components are 0 everywhere in space. All right, so this is the field in this case. Okay, so now let's see what happens if I perform the limits approaching 1 from inside and from outside. So these two limits. This is the minus limit, and this is the plus limit. So when we do that, we obtain rho naught over 3 epsilon naught times r in the limit to r plus. So I want to see what happens at this capital R. Here I approach from minus, so I need to use this equation. Okay, ur. So this simply gives us rho naught over 3 epsilon naught capital R ur. Let's do the limit from r that goes to capital R plus instead. So we need to use this other equation in this case. Rho naught over 3 epsilon naught capital R cube divided by small r squared ur. And guess what? In this case, we obtain r cube over r squared in the limit, so we obtain exactly the same result. Which means, in this specific case, we can close this parenthesis. Oops, exactly what I didn't want to do. We can close this parenthesis with brackets. We can close this parenthesis with brackets. Okay? In this fashion. Bracket, bracket. Because these two limits are exactly the same, which means this field is C naught everywhere in space. It's continuous. All right? So in this case, it seems apparently that we have a discontinuity. We have a surface, but we go from a volume density, which is defined everywhere in a volume, so something, 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 and nothing. When you have something, nothing, like here, you can actually prove, I do it in the notes, when you have something, nothing, actually is the same as having rho C naught everywhere in space, which means we can even use, it's okay to use the curl or the divergence, are all well defined. So you can use case 1, basically is well defined. And in fact, the field is continuous. Whereas, in the case of nothing, surface, nothing, case 1, it's not okay. All right, and I'll let you think about the derivatives of this field in Piazza. All right, so to recap this video about examples, we have done 2 examples where we have nothing, a surface distribution, nothing, the infinite plane of charge and the charge shell. In this case, we end up in case 2 of Maxwell's equations in electrostatics, which means there is a discontinuity for the normal components and a continuity, as always, for the tangent components, which in both cases were 0. So when you have a something, nothing, like in this case here of the hard sphere, I proved this in the notes. This is a new special case, which is called case 3. In fact, it is true that the field is continuous. The field is continuous at this point, capital R. However, I let you prove in Piazza what happens to the derivatives of the field. Are those continuous? That is, can we define the divergence of the curl in proximity of this point? Can we do that? That's the question for you. So in this region here, can we define properly the, let's say, curl of E in this neighborhood? Okay, think about that. Well, it's a new case, it's case 3. It does not belong to case 2 because the field is continuous. So it's there is a stark difference between these two, but yet you cannot use the differential form because of the derivatives. Think about that, okay? So this is called case 3. Whereas if we go back here, okay, in this case, when you have nothing, a surface nothing, which was the same for an infinite plane of charge or for a charge shell, in this case 1, you cannot use it, you need to use case 2. Okay? Case 2 is the one you want to use. That's it.